Alright gang, here we go. So this is Chem 2 Unit 4, talking about aqueous reactions, so on and so forth. Pulling up my periodic table, helps if I can spell it correctly. Alright, so in this unit we're going to be talking about all sorts of chemical reactions that all participate in aqueous reactions. Alright, so this kind of takes every little chemical reaction we'll be focusing on, and we talk about just a little bit of each one. So like we talk about precipitation reactions, and we talk about acid-base reactions, we talk about redox reactions, we talk about making solutions. Alright, so there's quite a bit in this chapter, and it kind of comes at you really fast, so make sure you really zone it in here, paying attention. This first video is going to be pretty short and sweet though. Should be a lot of review here to start. Alright, so solutions are defined as homogeneous mixtures, okay? So remember, homogeneous means same throughout. Same throughout. This should be review, right? Same throughout of two or more pure substances. So essentially, if you have two things, you mix them together, and they become a homogeneous mixture, then you have a solution. So a lot of times this takes place between two things that are in a liquid state, or sometimes a solid and a liquid. All right. So anyway, so this is our solution. The solvent is the one that you have the most of, and then everything else that's dissolved in there is called the solute. All right. So in this picture here, we've got methanol. These are these CH3OHs right here, and water molecules. There's way more water, so that means the water is the solvent, and the methanol is the solute. All right. So specifically, when water is the solvent, we call it an aqueous solution. Aqueous for water. All right. So ionic compounds dissolve by dissociation. So remember, ionic, okay, is a metal with a nonmetal. All right, metal with a nonmetal, and they dissolve by dissociation. Okay, so what's going on here in this picture? This is dissociation. So we've got a block of sodium chloride, all right, NaCl, and so essentially what happens is the water molecules will come in and surround these. So right here we've got a chlorine, right, and chlorine's got a negative charge on it. Oops, it's going to yell at me. We've got a negative charge on that chlorine, and that chlorine will end up getting surrounded by the positive end of our hydrogen, of our water. Remember, water has kind of a shape like this. You should have talked about this at length in Chem 1, and it's got this shape where we've got a negative end over here and a positive end. Maybe I should, partial negative, partial positive. But anyway, and so the positive end, meaning the hydrogen end, will surround the chlorine and will help pull it away. Okay, so it surrounds it, and then they just kind of float away. And the sodium, the opposite things happen. Remember, these little purple balls are your sodium, and they're positively charged. So the negative end of the water, which is the oxygen end, kind of surrounds the sodiums. Anyway, and so they kind of like break up those ionic attractions between the sodium and the chlorine, and then they can just float away off into the solution. So that's how dissociation occurs. So this will happen with ionic compounds. Remember, so this is metal with a nonmetal. Sodium is a metal, chlorine is a nonmetal. Okay, molecular compounds interact with water but do not dissociate. Some do dissociate, like those that are like extremely acidic. Molecular compounds will actually dissociate, but for the most part they don't dissociate. So when a molecular substance does react with water or that dissolves in water, then we call that solvation, or sorry, we call that just dissolving. Okay, and so anytime anything dissolves, we call it solvation. So this act of chlorine and the sodium being surrounded by the water molecules, that's called solvation. And same thing here with these methanols being surrounded by the water, they're being solvated. Okay, so so essentially here's the big takeaways. Ionic compounds, okay, they dissociate. That's the correct term, because they dissociate from each other. All right, and then the molecular compounds, they dissolve. Okay. All right. Technically, dissociating is dissolving, but like dissociate kind of gives you a little better, clear idea of what's going on. All right. So electrolytes and non-electrolytes. All right. Electrolytes. The name comes from something meaning they'll conduct electricity when they're in water. So when they were first discovering these, they discovered when these things dissolved in water, some of them would actually make the water able to conduct electricity versus not. Okay, so so things that are electrolytes are things that when put in water they dissolve and then they help conduct electricity. So we can have strong, weak, and non-electrolytes. Weak and non-electrolytes. So this is kind of an important table here. We'll talk about this table more when we get to the acid section of our unit here. All right. So an electrolyte is a substance that dissolves into ions when it's dissolved in water, so plus and minus. And you should know now that electricity is really just electron flows, and so having these extra electrons and these positives in here will make the electrons able to travel through solution. Water itself is neutral. It might have a partial positive and partial negative end, but it's not. It's actually pretty neutral, right? And so anyway, so all ionic compounds are strong electrolytes. Okay, and all strong acids are electrolytes. And when we get to strong acids, you'll have this guy. We'll have some 7 strong acids for you to memorize. Weak electrolytes, no ionic compounds are weak electrolytes. Weak acids and weak bases are defined as weak electrolytes. Strong bases can be a strong electrolyte or a weak electrolyte, just kind of depending on how they act like a strong base. So like a metal hydroxide, those are a strong electrolyte, but some of the other strong bases, not so much. All right. And then anything else that's not one of these 3 things would be a non-electrolyte. Okay. So anyway, non-electrolytes may actually dissolve in water, but they don't dissociate into ions. So for example, like sugar, right? Sugar here. The sugar dissolves in water. That's an important thing. Otherwise, we wouldn't have like Dr. Pepper and things like that. So sugar dissolves in water, but it doesn't dissolve into dissociate into ions. It just stays as that glucose molecule. All right. So here's another picture of picturing what electrolytes do. Okay, so here we've got pure water. We've got it hooked up to the battery. Notice that the light bulb is not coming on. Pure water does not conduct electricity. They added a non-electrolyte, so that's the sugar. Okay, that's your sucrose. Dump that guy in there, still doesn't conduct electricity. And then adding a strong electrolyte like sodium chloride, that's an ionic compound, so it's a strong electrolyte. Adding that guy in conducts electricity, and your light bulb goes off. Pretty exciting stuff right there. Okay. A strong electrolyte always dissociates completely when dissolved in water. And now, if you remember back to Chem 1, we learned about how we can have reactions. Remember this guy? We can have a reaction that kind of goes one way versus the other. And you can kind of have a back and forth trade. Remember, we call that being at equilibrium, and we use that arrow to represent going in the forwards reaction and the reverse reaction. So same kind of thing happens here. We've got HCl, and it's dissociating in H plus and Cl minus. HCl is a strong acid. Okay, so it's a strong electrolyte, so it dissociates completely. Weak electrolytes dissociates only partially. Okay, so they reach like a chemical equilibrium where it's got part of the original and then part of the ions that it dissociates into. So this is acetic acid right here. Acetic acid is a weak acid, right? So according to our table we just looked at, we know that's a weak electrolyte. But really what that means is it's only partially dissolving or dissociating into its ions. So you get H plus and then CH3COO minus, which is acetate anion. Okay, so when you put that guy in solution, part of it is going to be H plus, part of it's going to be acetate, but part of it's still going to be the acetic acid with that H attached to it. All right, so let's do a practice problem or two here. Okay, it says if you have an aqueous solution that contains 1.5 moles of HCl, how many moles of ions are in the solution? Well, you should know that this guy will turn into H plus, and this guy plus, and this guy will turn into Cl minus, and so we know we'll get 3. All right, but let's do this using skills that we learned last chapter, just to prove to ourselves we know what we're doing. So we know from the last slide there that HCl turns into H plus and Cl minus. Okay, and so I need to know how much of these ions am I going to make. Well, I started with 1.5 moles of HCl, all right, and I'm going to convert this to moles of H plus. So I put moles of HCl in the bottom, put moles of H plus in the top. All right, for every 1 mole of HCl, I get 1 mole of H plus, so I have 1.5 moles of H plus. And you can kind of see I'm doing the exact same thing again. I say 1.5 moles of HCl, and I'm going to convert that into moles of Cl minus. So HCl goes in the bottom, moles of Cl minus goes in the top. They're in a 1-to-1 ratio, so I get 1.5 moles of Cl minus, and I can add those two guys up together to get my 3.0 moles of ions. Pretty slick. So we can solve that using stoichiometry, but really we can just look at this guy here and look at how many ions I split up into. All right. So if you were to draw diagrams representing aqueous solutions of these guys, so we got 4 different things, how many anions would you show if each diagram contains 6 cations? All right, so let's just do a couple of these. So we got NiSO4. Well, we know that this guy, this is the cation, and this is the anion here. So we'll say I'm going to get Ni2 plus and SO4 2 minus. All right, so if I'm going to get 6 of these, then I know I'll get 6 sulfates out the other side, so 6 anions. All right, we could do a stoichiometry. We could say 6 moles of, or 6. Let's see how many anions contain 6 cations. So I could say 6 nickels gives me, it'd be in a 1-to-1 ratio of sulfate. Okay, let's try the next one here. So calcium nitrate, so CaNO3 2. All right, so this gives me Ca and 2 NO3s. So for every 1 calcium, I get 2 nitrates. So, and I should probably put the charges here. I'm going to be a cool kid. So it'd be, so I get, for every 1 calcium, I get 2 nitrates. So that means I get 12 anions. All right. Let's try this one, and then we'll be done here. Sodium Na3PO4. All right. So I get 3 sodiums and 1 phosphate. So that's a 3 minus. All right, so for every 3 sodiums, I get 1 phosphate. So if I have 6, that means I'm only going to get 2 anions. All right, and if that one confuses you, do the stoichiometry here. So we know we have 6 sodiums, right? And we could put, all right, for every 3 sodiums, and I'm getting these numbers from my coefficients, right? I get 1 phosphate. So 3 sodiums, 1 phosphate. PO4 3 minus, so 6 divided by 3, that gives me my 2 phosphate ions. All right, 3 minus. All right, oh, we might as well do the last one just for grins and giggles. Let's do it up here though. All right, so we get Al2SO4 3. All right, so this guy is going to give me 2 aluminum 3 pluses and 3 S. Oh shoot. Might as well erase this guy. 3 SO4 3 minuses. 2 minuses. Who's writing this thing? Who's in charge? 2 minuses. All right, and we're going to get 6 cations. So what I would just do here, I know this is going to be a 3 halves, right? But let's just go ahead and do the stoichiometry just to make sure we're doing everything right. So it'd be 6 Al3 plus. All right, and it's in a ratio of 2 to 3, right? So 3SO4 2 minus 2 Al3 plus. All right, so 6 divided by 2 is 3 times 3, so we get 9. All right, SO4 3 minus 4 3 minus. So this guy would be 9 anions. All right. Let's see, solubility of ionic compounds. So you know probably from Chem 1 and before that some things form precipitates and some things don't. We can predict what precipitates we're going to form by using what are called solubility rules. All right, this is the one that's in our textbook, and so I gave you a copy of this, and this is what I'll allow you to use on the exams for now, I think. So anyway, let's just read through how to read these. So it comes in 2 halves, all right? The top half here is talking about soluble compounds. So everything in this list, it's all organized by the anion that it's attached to. So everything in this list is soluble unless it's with these things. So nitrate is soluble unless it's with, well, nothing, right? So sodium is always soluble. Same thing with acetate, always soluble. But chlorine, so say you have something attached to a chlorine, it's always soluble unless it's with silver, mercury, or lead. All right, bromine is always soluble unless it's with silver, mercury, or lead. Okay, sulfate is always soluble unless it's with strontium, barium, mercury, or lead. All right, the other half goes backwards. Okay, so these guys here, these anions here, are always insoluble unless they're with these things. So sulfide is always insoluble unless it's with ammonium, calcium, strontium, or barium. Carbonate is always insoluble unless it's ammonium or an alkali metal. All right, we can kind of keep going. So you got to make sure you keep track of which half of the period or which half of that table you're looking at. All right, so let's do a couple of these. Which of the following is insoluble in water? All right, so where it's always based off the anion, and I really should have Maybe I'll pull up a periodic solubility chart here. Solubility chart. All right. So solubility chart. All right. So here we go. So we always got to identify the anion that it's attached to first. Okay. So the anion here is the sulfur. Okay, so we go to our solubility chart, we find sulfur, we say sulfur is always insoluble unless it's with an alkali metal or ammonium. Well, this is ammonium, right? And so this guy will be soluble, all right? Carbonate, find carbonate, all right? Carbonate is always insoluble unless it's with a group 1 or an alkali metal or ammonium. Calcium is alkaline, earth metal, so this has got to be my answer, but let's check the other ones. Anion here is hydroxide, so we find OH minus. Hydroxides are always insoluble unless it's with any of the alkali metals, calcium, barium, or strontium, or ammonium. So sodium is an alkali metal, so therefore this guy will be soluble. We find sulfate. Sulfate is always soluble unless it's combined with silver, calcium, strontium, barium, or lead. Okay, so maybe there's more than one right answer here. So silver is always, let's see here for a second. Sulfate. See, that's funny. I looked up a different one online, and they have silver listed here. So according to our textbook, silver sulfate is soluble, but according to this online list, silver sulfate is insoluble. They also have calcium on here as well that's not listed in our book. Huh. Anyway. Okay, and then lead acetate, acetates are always soluble. Okay, so anyway, so that's it for this guy here. You can do this one, but this is just more of the same practice. You're just doing it. You just have to convert it into there, figuring out what the anion is there based on the name. Anyway, do your homework problems. Let me know if you have any questions, and get ready to have some fun in the next part.